Hey everybody, this is our video solution to problem 1 from the Fall 2021 Math 302 final at Cal State Fullerton. So this problem is all about testing whether a certain subset of the ring of 2 by 2 matrices over the integers is an ideal. So the subset we're looking at is all the matrices of the form, okay, the top row is all zeros, and then the bottom row can be any integers we like. And we want to know, is this an ideal? Well, in class we gave a list of criteria that we needed to check in order to show something was an ideal. So the first thing on that list is we had to show that 0, right, is an element of the ideal. Now in this case, when we say 0, right, 0 is equal to the 0 matrix. Okay, so that is the 0 in the ring of 2 by 2 matrices. And so this is really just a matter of, does this fit the form? Ah, well, yes. 0, 0, something in Z, something in Z. Yes, 0 is something in Z. So, yeah, this is very clear, right? So since, right, 0, 0, 0, 0 is definitely an element of I. Okay, what's the second thing we have to check? Oh, right, closure under addition. So if I have two matrices, A and B and I, then I need to check that A plus B is an element of I. All right, so let's check that. So let's see, if I have some A, it's going to look like, I don't know, like an S and a T. So let A equal 0, 0, ST. And B, how about 0, 0, I don't know, UV, where S, T, U, and V are all integers. Okay, now we need to check the sum. So we have A plus B equals 0, 0, S plus U, T plus V. And yeah, right, S plus U and T plus V are elements of the integers, so this really is an element of I. So this implies A plus B is an element of I. All right, what's the third condition? We need to check if this subset absorbs multiplication by elements in the entire ring. All right, well, let's give it a try. So we need to show if A is in I, and how about we'll just call it M, is in the ring of 2 by 2 matrices over the integers. Then, well, we actually will have to show both directions, all right? So absorption has to work on the left and the right. Normally, if we were working in a commutative ring, this is not something we worried about because left and right multiplication are the same. But since we're working in a non-commutative ring, we have to check both directions. So then AM and MA have to be, in this ideal I, or this proposed ideal I. Okay, so we want to prove that. So let's see. Well, we already have an A up above. We'll just copy that, 0, 0, S, and T. But now my M, that can be any matrix. So let's just call this, well, I don't want to use A because that'll conflict with that, so we'll just call it like C, D, E, and F. All right, so let's try multiplying these things. Okay, where, oh, by the way, here, we'll put in here, right, again, S, T, C, D, E, and F are all integers. Okay, so if I do, say, AM, so this will be 0, 0, ST times C, D, E, F. And that's going to equal, let's see, 0, 0. Okay, 0, 0, beautiful. And then I got stuff. All right, SC plus TE, and then SD plus TF. And I don't really care a whole lot what that stuff is, because I already know I have zeros in the top. These are definitely integers, and so I have something which is still in I. All right, well, let's try the other direction. So if I have CDEF times 0, 0, ST, let's see, I get C times 0 plus D times S, C0 plus D times T, E0 times FS, E0 by FT. Oh, and this looks like a problem. The top of this matrix doesn't obviously look like zeros. Okay? And that would be a problem, because if it's not zeros, then it's not in I. Now, I can't just stop here, right? This is where a lot of people just say, oh, look, this is not an element of I. Well, it could be. What if D is 0? If D is 0, then these are zeros in the top. So we need to, before we conclude that it's not an element of I, we need to give an explicit example. And in fact, the explicit example, right, we just need to make sure we don't get zeros in the top row. So I could do that by saying, well, let me make sure my D is like something like 1. All right, so I'll put a 1 here. And then what else? Well, I need S and T, at least one of those to not be 0. All right? In fact, if I make my S equal to 1, and my T, it doesn't even matter, because now I'll have a 1 in that top position. All right, there's my DS. Okay, so does it even matter what I put anywhere else? Not really. I put a 0, 0, 0, 0, 0, 0, and then the product is going to be, hey, look at that. Let's see, 0, 1, 0, 0, 0, 0. Yeah, okay, we got lots of zeros. And this is definitely not an element of I, even though that's an element of the ring, and this is an element of I, but their product is not in I. So from this very last bit, we conclude I is not an ideal in the ring of 2 by 2 matrices over the integers. All right, we'll see you next time where we show that something is an ideal.